Yeah, one GPU for that. That's very old. A very old GPU.
Okay, so the last time we talked about for solid state drives, we typically would need an FTL to manage the data mapping, remapping, garbage collection because of the weird characteristics of flash memory that you can only erase in a unit of multiple pages, and each of the page they have limited amount of program erase cycle. So what turns out is that every time before you go into the real chip, you have to go through a lookup table that consists the content of the current location. However, if you want to update, you cannot or you should not directly update the page where your content that is currently located. Instead, you might need to copy stuff out and rewrite them. Well, so you might need to garbage collect them and then write your content to another location. So that's what why we need an FTL. And the last time we also talked about PCIe itself is a packet switch network. And turns out if you have packet switch, then or say if you have that kind of like multi-layer concept, you can actually put another layer of protocol inside as a payload of the lower level protocol. So in fact, on top of PCIe, you can add any other new protocol. So like NVMe is one of them. And these days, if you are familiar with the high-speed I/O, you probably also heard about CXL. CXL is also another protocol you can carry on top of the PCIe interconnect. And all you need is that in your content, you just need a few headers. So for example, what we learned here is that the last time, like if you check the headers of NVMe, it actually contain a few things like this opcode. The last time we talked about the NVMe driver, and this is where you fill those opcode in. And the command ID would give you an idea, the sequence of your command, like the order of your command. So if you need to reorder them, based on this command ID, you know who comes first. Because you remember that, right? Like for NVMe, the purpose is that we can perform multiple channel access all the same time. And instead, like serial ATA or all the conventional hard disk drive, they cannot have that feature. So that's why if you buy an SSD, we typically would suggest you go with the NVMe instead of a serial ATA. The reason is because for serial ATA, you can only execute command one back to back. Instead of for NVMe, you can issue multiple command altogether. And but the thing is that if you issue all the command altogether you want to ensure the correctness of your execution result, you definitely need some sequence number, which is the command ID here to help you. And there is also a namespace ID. So one thing that NVMe introduced, which it doesn't exist in other systems, is this, the namespace concept. So you can consider namespace as a virtualized unit of hardware. So the reason why we want to talk about virtualization is because right now we are in an era that a lot of applications are based on cloud. And a lot of the storage, they are aiming at providing storage for cloud services. And but the thing is that we don't want to create a separate hardware for each different cloud instance. Otherwise, it lost the original purpose of virtualization. However, without a physical separation of the hardware, it makes it different for the system to manage the resource management. So it turns out NVMe introduced this namespace concept for that purpose. And it's always not a bad idea to have a reserved area. And in fact, a lot of innovations of NVMe later on use this reserved area to carry additional information that is needed. And there's also metadata, which tell you about for each file, we have the metadata. So this is pretty much like a metadata buffer. And there is a PRP list here. So the PRP list in NVMe, they basically talk about how many, the list of sectors of your content. So, and the reason why we want this, remember the last time we talked about the extent-based file system. So the basic idea of extent-based file system is that for each file, we allocate space as a linked list fashion. So what does that mean is that although it's a single file, your file might not be your file might not be consecutive in your logic blocks addresses. So it turns out, but sometimes we also need to form lot transactions. So the only thing, so what NVMe does here is that, so we allow that lot transaction to be formed in a way that you can provide a list of sectors that this command should access in addition to the starting location. So this is pretty much like, okay, you give the storage device a set of address, a list of address with a single command, so that you can reduce the overhead of this command and header to further improve performance. And also the length, meaning how many blocks should I access through this command. And depending on the support of your vendor. So although in theory, you can have up to 2 to the 8 blocks in your length field. However, it depends on the support of your vendor. Some of them doesn't support that much. So it also limited the larger size of the transaction you can form. And in fact, a lot of the data center SSDs, they perform better performance because the hardware support larger transactions so that you can support larger bandwidth. And some of the control beds and data set management features and some of the tech that help us to figure out what we want to do with this NVMe command. So saying that if you have an application that needs to access the storage, here is the big picture regarding how we make that happen. So nowadays, in your application, you typically would use like fread, fwrite, these kind of high-level functions instead of the direct access like using the block address, right? So, and the reason why you can use file name instead of direct address is because we have the file system. So by just giving the file descriptor, you are able to let the file system translate the command to become a set of logic block addresses that you want to access. And then with file system translate that, with library translated your command, they will go through an IO Kado system to form the real system command, which we already show you in the last time through the code demos that we have regarding how the IO Kado system work. And then the IO Kado interface would translate that command and feel, and as the last time we show, right? We do it like byte by byte addressing assignment to form the real command. That would later on pass to the device. So that's actually how your application reach your device nowadays. And and the thing is that in our system, we always want to ensure fairness. And although in your operating system paper or in a lot of papers, you read a lot of policies that try to ensure fairness. But to be honest, if you are familiar with the real implementation of operating system, you will figure out that those algorithms that you read in a paper, they are never implemented because they are way too complicated. And in fact, if you run this algorithm, the overhead is fairly large. So they turns out to be something that's only possible on a paper, but never being realized. So to ensure fairness, the real practice right now still falls on variants of round robin. And this is also true for NVMe. So the idea of NVMe in terms of this is that your controller would use a round robin manner to periodically poll each of the host queue to see if there is anything that needs to be addressed. So, and each host queue pair is coupled with your processor. So the number of processor cores pretty much determine the number of command queues that you have, queue pairs you have. So what does that mean is that most of the time, if you just run a process, then the process is only going to use one of the command queue pairs. So what does that mean is that the process only gets like the 1 over the amount of processor you have this kind of share in accessing the device, which by no means you can fully leverage your bandwidth. So modern NVMe driver, they adopt this multi-queue models is that as long as I found there are unutilized processor queues, queue pairs, I can use work stealing as a policy to steal the commands from one queue to another to fill the underutilized bandwidth of NVMe. Okay, so this is, again, the PCIe interconnect. And the reason why I want to remind you about this, because if you remember what we talked about regarding this PCIe interconnect, right? If you check the command format that we have seen before, right? What PCIe really need is a memory address, right? Like this memory address to tell people where's the destination of your device, right? Where's the destination of your device? So if I have if saying that if I have one device, and if you remember, right, during the boot process, all the devices are supposed to get a DMA address for its buffer for its command signaling. So in that case, there is a possibility that there is no reason why everything has to be intervened by the CPU. Do you agree with that? So now I'm going to ask you a question. So if you are the engineer, how can you let the SSD communicate with GPU directly? And why does this would make sense or not making sense?
Special but then if we want to send it directly to GPU and SSD, you need to somehow like do like put a format address that will SSD so the SSD knows where to send that data to. Like again, it needs some kind of like instead of going through a DRAM buffer, we need to somehow route it yeah. But it needs to know like where the space. The space in GPU memory what data where to find what data. That's like a location. But it makes sense in certain like it makes sense because again you just stick your file into like major basically start like and then oh I actually for all searches you no longer have a yeah they have to they rather than the general case of just sticking like having a specific like PCIe, right? To the my next question is just basically communication because are we gonna say like communication is kind of a hard part because if you because the GPU is like not really meant to do like a lot of like parallel computations, right? So for like let's say we have all these parallel nodes, right?
All right. So how can you let SSDs communicate with GPUs directly? First of all, why can't they communicate directly right now? What's the problem with it? What's the problem right now? Isn't there a direct wire? Yeah, but you don't have to go through the CPU, right? But right now, how do you perform GPU to SSD data movement? How do you do it?
CPU initiates it packets.
CPU, so remind yourself, right? How do you move data from a file system to the GPU nowadays? How do you do it? Do you remember that? Yeah, right now you have to move to memory, right? Like you have to use fopen, right? Read a file, store it in a buffer, and send it to the GPU, right? And from fopen, you store your data from SSD, load your data from the SSD to the memory buffer, and use CUDA main copy to get data from your main memory to your GPU, right? That's the current model, right? Is it direct communication? Okay, but why do we have to do it, right? So right now, what we are doing is we have to go through the CPU, get the data from the DRAM, and go to the GPU, right? How can we implement that? Specialized hardware? What do you mean by? So, okay, let me clarify this. Right now, we have to go through the DRAM, right? Can we at least not going through the DRAM? Can we at least not going through the DRAM? What? Okay, but how come we didn't do that right now? What's the problem?
Security?
Why?
Because now, like, actually, I never mind. We might have to change the programming practice in which we allocate both memory and both DRAM and GPU at the same time.
Okay, so say it again.
So I think in CUDA, we always, when we allocate memory and GPU, we always allocate at the same time in DRAM.
Mm-hmm.
So we will have to change this like practice.
So how does that correlate it with the problem that I talked?
But because allocate the memory in DRAM so that there's like.
Is that true?
I think it is.
No. When you do CUDA-malloc, you can pick that I only want to alloc a device buffer. And in fact, that's the most of the time what we did. There's no practice saying that you always need a memory buffer that's aligned with your GPU buffer, right? And you can also create on-device buffers, right? Like saying that if today I want to use half precision, you don't convert the number into half precision on the CPU first. Instead, what you do is that you copy the data from the CPU memory to the GPU device memory, and then you allocate a GPU device memory buffer, which you won't see the same version on your main memory, and you convert the floating point into half precision, put them into that buffer, right? So what you are saying is actually not true. Okay, what else? What's preventing us from making this direct communication nowadays? Originally, not nowadays. CPU controls everything, okay, including what? Okay, file system, the abstraction is maintained by the CPU. So how does that affect you? And you say CPU controls memory. To what degree would that limit? Virtual memory in what degree? You can't directly communicate with physical memory. Why?
You don't know what's there.
We don't know what's there? Is that the only reason? No? Okay, so here's the thing. I feel you all know some of this part of this answer, but this is actually, first of all, there's no reason why you cannot do direct SSD to CPU transfer now if there is no operating system. So the whole problem is because we have operating system. So what aspect in the operating system would prevent us from doing that? So some of you talk about security. Some of you talk about virtual memory. Those are all the reasons. So first of all, security perspective. That's maintained by the operating system where we want to isolate process from process. So that's why we create virtual memory abstraction, right? So, and because of a virtual memory abstraction, you need the operating system to translate your virtual address, which is within each process, to the physical address. And that includes all the physical addresses that are mapped to the operating system. So you cannot let the application directly find out. So the thing is that because all your application is run within the virtual address space, so they have no way to generate a packet that would destinate to a physical location that you want, because everything is translated through the operating system. And who runs the operating system? The CPU runs the operating system, right? So all the NVMe commands, all the PCI commands, they must be issued by the processor first, right? And the original design in the operating system, they have no consideration to support this P2P transfer. Because if everything has to go through the operating system, it makes it so easy for the operating system to maintain all the protection and security, right? So now, if we want to add, so sounds like it's just because the operating system lacking that feature. So if you are the operating system designer, or you have the ability to add a kernel module, what are you going to do to make this P2P happen? What's missing? Okay.
Wouldn't you need like a portion of the operating system to now be executing on, not executing on the GPU, but you need the GPU to be able to kind of translate things?
Is it reasonable?
It's not. I guess, are we
Right.
allowing the CPU to just say, okay, send this from SSD to GPU directly?
You got it, right? So the thing is that currently there is no driver. Well, by default, there's no driver doing that, right? So you need a driver that is able to set the destination address to the GPU when you perform an NVMe command, right? So first of all, right now, all the NVMe commands, they can only send to main memory buffer. You have to modify it to become available to the GPU buffer, right? But what's wrong? But what's the problem? Or why do we originally not doing it? Who is preventing us from making that happen? Is operating system, is Microsoft or Ubuntu the only one who is going to blame? What are the missing part? Okay, so here's the thing, GPU has to support. And GPU has to support in what degree? So first of all, the GPU driver must provide a feature that allow them to map any GPU device memory, or at least the bar, the basic address register, being available to map to the virtual address space of your process. Because right now, you can only use the CUDA functions to perform any manipulation of the GPU. And that's not supporting the feature of mapping its own physical location as something that is visible from the application directly, right? If that's true, you should directly be able to print F on any of the GPU location. But right now, what you do is that if you try to print F from a GPU address, you are going to see all zeros. And the reason why is that is because those addresses are not directly addressable from the running process, right? So first of all, the GPU driver has to support some of the features that allow the operating system, virtual memory system, to directly manage the GPU device memory. And it wasn't possible in the past because the GPU should not maintain, because it also means that you have to make your GPU device memory pageable through virtual memory abstraction. And previously, GPU don't want to do that because it's already pretty slow, and the communication have to go through the PCIe. And it also means that I need a TLB on the GPU. And the thing is that the GPU itself doesn't support the page granularity as the virtual memory management. If you know well regarding how GPU manage their virtual memory, they are using the concept of segments instead of paging, right? So they don't actually support paging, right? So to make that happen, the GPU device driver, they must support some sort of mapping ability to map a physical location into the process paging. Question?
What's the difference between segments and paging?
So segments means that I give you a starting address and all of them are consecutive. Right? And this makes sense for GPU because typically you just allocate a big buffer. Right? Okay, so if I want to implement, so this is the current model, right? I always have to go through the GPU. So if you really want to implement the direct transfer, here's what you should do. So first of all, right, you need a spatial driver. So what will happen is that from the application perspective, I need a spatial function, library function call that would help me to consult the file system regarding where is the source or destination file. And then you grab this data and tell a spatialized driver, let's call it P2P driver right here. And this P2P driver, it should consult the GPU runtime. And by consult the GPU runtime, what it does is that it maps a segment of GPU address to the base address register in your system. Because each device has limited amount of, well, so the thing is that, okay, one of the reasons why GPU doesn't want to use a paging system is because thinking about the giant memory array on the GPU. And you already learned the paging has a huge overhead in page tables. So GPU doesn't want to do that, right? So the thing is that GPU don't have a page table. And even though I want to make it pageable, I only want to do it with a limited degree. So nowadays, like NVIDIA GPUs, they only allow 256 megabytes of memory to be paged by the system main memory. So in the virtual memory abstraction, and this region is called base bar. So when you see this bar, it means those are the addresses that are directly accessible by other device on the PCIe. And the thing is that this bar, you can remap. Okay, so the bar address in the system main memory perspective, it never changes. So once you assign a bar address to a device, this address is mapped to your device. What you can change is that the window of this consecutive 256 megabyte, where do that map to your device memory? You can change that window, right? So what you have to do is that you have to consult the GPU runtime to consistently change that window map to the destination device memory address where you want to access data from or copy data to. And after that, you register that new address in a PCIe root complex, and then report that address to your P2P driver so that you can let the NVMe driver know, here's my new destination address. And then you send this driver through PCIe controller to the SSD controller, and then you can directly send data to the GPU, and the other way around, right? And the reason why we want to do this, right, because don't forget the second part of the question is that why does it make sense, is that with the GPU or CPU speed up the computation, a majority of applications that from the Rodinia benchmark applications, we actually spend 54% of the time on average in just moving data from the storage to the GPU device, right? So, so that's why we really need a direct access. So a paper that I published in 2016, I actually created a driver like that, and this is the measurement that I get. So the number looks a little bit slow from today's perspective, but don't forget that was a paper about 10 years ago. So the speed of your solid state drive and the GPU is aligned with this, the high performance ones at that time. So you can see with direct communication of NVMe, you are actually going to have larger bandwidth compared with a buffered situation. And as we said, NVMe driver, you can actually maximize its performance through multiple queues. So at that time, we try to use 4 different queue pairs, and that would give us around 1 gigabyte per second performance between the SSD and the GPU through the GPU through the main memory buffer. And if you do the right thing, then combined with 4 threads, you are able to run it at 1.2 gigabyte per second. So it's not a lot. It's not a lot. Right? So, and let me show you, and that was our research paper at 2016, and apparently NVIDIA knows this thing has a value. So let me, so nowadays the NVIDIA also have a, also implemented their own version of the GPU direct, GPU SD direct solution called GDS. So let me show you this demo about the GDS. So the right-hand side is the triangle version of the, let me see. Yeah, the right-hand side is the triangle version of the code. So let's compare the left-hand side and the right-hand side. So the right-hand side is what you do right now, is that whenever you want to read a file and send it to the GPU buffer, you need to open it and create a main memory buffer using manlock, right? And in this way, you are creating a main memory buffer, and you copy the stuff, and then you use the CUDA manlock to allocate a device buffer. And with that, you can finally start copying stuff from, and then when you read a file, you have to read the content to the main memory buffer, and which we have the function code perform the read here, read fd mm buffer and buffer size, and then you can do the CUDA main copy. That's how right now you get your data into the GPU memory buffer, and then finally you perform computation, and this is what you do right now. And the left-hand side is the GDS version. So as you see, you cannot directly create a file descriptor as what you used to. Instead, you have to create a GDS descriptor, which you use the spatial function call and you use a spatial data structure and register that to your like a cool file functions, right? So in the function here, from what I can tell is that they will. You remember the last demo, we also give you a program called go sector list, right? Get sector list. So this, based on my personal experience, what this function would do is that they use this file descriptor to get all the sectors belong to this file and in the CUDA runtime. So then what happened is that you still have to allocate a GPU device buffer, and then instead of reading the file using the rate file code and use CUDA main copy, right now it's combined as one CU file read, and you directly go through the device pointer. And here you don't see anything that's related to you don't see anything that is related to the main memory buffer, right? So which tells you that there is not really a coupling between you must always have a memory buffer to have a GPU device memory buffer. And then you still can do the rest of the computation as usual. So then let me show you this demo real quick, and let's see what the performance would look like. So right now, for this demo, I try to read. So this is the GDS version of the code. I try to read this amount of bytes. So this is like 1.2 terabytes, and reading this 1.2 terabytes only use 355 milliseconds, which give you a bandwidth of 1.8 gigabyte per second. And now I'm using this triangle version, which is using a main memory buffer. And as you can see, it takes almost triple amount of time for file reading, and your bandwidth is only 700 megabyte per second. So you see the power of the GDS. And the GDS tool also have quite a few. It also, if you install the GDS, you can see a GDS IO. And this GDS IO, they would give you a few interesting configurations. So for this one, this is the version that use one single thread for GPU Direct. And as you can see, if you use one single thread, you are getting with their optimal version. Well, so this one, because they don't actually read a file. So you can assume that they are just reading consecutive locations on your solid state drive. So that's why your performance is such high. So you can get like 2.78 gigabyte per second. And the second configuration is that you can do you can have deeper queue depths, and then as you can see, you can get your performance up to 3 gigabyte per second. And you can also use you can also test compare it against with the GPU goes through the main memory, and you can see your throughput is also not bad if you use multiple threads to optimize it, right? So So here's the thing, right? So now, again, based on this performance measured, do you think it's always a good idea, or is it a good idea, or is it necessary to have GPU direct? Under what situation do you think you would need GPU direct? Under what situation do you think you don't need GPU direct?
I think like if you have something doing like HPC, like high performance computing, where you're moving memory, doing calculations, and you want it to be fast, you don't necessarily want it to like go through like even that.
Where are you going to perform the computation?
Well, on the GPU.
Then your case is saying that if I have GPU performing the computation, you want GPU direct?
Not always, but like in that specific application where even like just a small increase in throughput is a lot, I would say in that case.
Are you sure?
No.
Okay, what's the drawback? What's the benefit?
The benefit would be that you're not using the CPU as much.
You are not using the CPU as much.
So if your CPU was overloaded and then you have GPU direct, the gain would be very high.
Okay, if the CPU is overloaded, then you have GPU direct because you have fewer amounts of command that has to go through the CPU, so it will be higher performing. What else? So that's the benefit. What's the main benefit of that? You can do more stuff on the CPU, but what if today I'm only using the GPU for most of the stuff? And why don't we just always use, like how often, like before this lecture, how many of you ever heard about GDS? Not at all, right? So it's something that's not that popular. How many of you ever noticed that there's a cool file? Right? So it sounds like this is a good, okay, so the thing is that I've been doing research for quite a while. And then I have enough of feeling that I made a lot of useless stuff. And I did this project because my advisor asked me to, right? And now I grow up and I figure out that's probably a waste of my time doing this, right? Like even NVIDIA, they spend a lot of money doing this, but this never flies because we never know why do we want to do this, right? So what's the benefit and the drawback of doing this? Why not doing this? And you have to rewrite all your file, right? File system call, right? Instead of just so it's not a plugin upgrade, right? So the thing is that a lot of computer science innovations, they failed because you have to modify your software. So if you could have something that don't let the original programmer to modify their software and everything works as fine as what it used to be, this one will fly, right? So that's why I really would like to see some of like the, unless, okay, so if you want something that you need engineering work and people would like to adapt it, you need to give people sufficient amount of incentives, right? But from the demo, is that sufficient? It's basically the same, right? So the thing is that if you have an optimized NVMe driver, you are only going to lose like 10%, well, 1% of performance in this way, right? Like on the third line or the second line. So you might wonder, okay, why in the very beginning here it shows this significant slowdown? And the thing I want to tell you is because the second demo, it's just used the default NVMe library, default file system library, which is not multi-threaded. If you enable multi-threading on this, you are able to get performance similar to this one when you are reading files, right? The original purpose of not doing is, well, so a few things you might want to do GPU direct communication. So, but let me talk about this, right? First of all, what's the main benefit of GPU direct communication? So some of you are talking about the CPU offloading. That's one. But none of you touched the main reason why we want this.
Latency?
Latency is one of this, but the thing is that as long as you start using GPU, you already don't care about latency, right? GPU is by no means for latency sensitive applications.
Oh, I mean like from transferring the memory, like it's faster to go directly.
Yeah, but the GPU has, if you do a good amount of double buffering, right? I don't even care about latency, right? What's the main problem? Under what situation you would like to use GPU direct? A lot of data transfer to GPU. Is that true? Or what do you think? So who is the bottleneck?
Oh,
PCIe is PCIe the bottleneck. So what's the current interconnect bandwidth look like? Do you guys have an idea? On PCIe, typically how many lanes, how many channels, or say how many bandwidths we allocate to each different device? We have a sufficient amount of demo last time, right? So you should have a good idea. For SSD, typically how many lanes? How many PCIe lanes? 4, right? So what does that mean? How many megabytes per second? How many gigabytes per second are we allocating to the SSD? What? No. 4 gigabytes per second. So in PCIe standard, typically if you are now following PCIe 3, each lane is 1 gigabyte per second. So 4 lanes means 4 gigabyte per second. And through the demo last time, none of the SSD has more than 2 gigabyte of performance. Gigabyte per second, right? So 4 is good enough. Some of you might be wondering that, oh, I see those like NVMe 4 or PCIe 4 SSDs. But if you check their spec, for those PCIe 4 SSDs, they either use PCIe 4 times 2 or PCIe 3 times 4. So they are only capable of utilizing 4 gigabyte per second, even though they claim they can use 4 gigabyte per second, but if you measure them, none of them really reach that performance yet, right? So 4 gigabyte per second. How about your GPU? 16, so what does that mean? 16 gigabyte per second, right? So from this perspective, who is the bottleneck? SSD is the bottleneck. So if SSD is a bottleneck, and if I have an optimized NVMe driver, and if I have a big enough file, at the end, you won't see that much performance difference between SSD and GPU, even though you go through the memory buffer, right? But under what situation you would think GPU direct SSD communication is a good idea? Well, small files, then the overhead is going to take over the whole thing, right? So it's less about the bandwidth, right? What else? You have a big server. Okay, one other situation, the big server would care about that. Yeah, but why?
20 GPUs all setting to one PCIe, that PCIe is going to get really full.
Okay, so here's the thing, right? The only reason, the only perspective that I would think this would be helpful is you have, again, your PCIe root complex is on the CPU, and everyone is connected to the CPU. And so, for example, if you have 8 GPUs, and you really want to save the traffic, right? If you have 8 GPUs that you want to perform like GPU to GPU communication, right? And if you always have to have everything going through the main memory, if you add this up, right, then it would just increase the total amount of traffic. So only when the traffic is a concern, you will need to do this, right? Well, you cannot have more PCIe, right? Because it's on a CPU, and every PCIe you have a physical LAN of it, right? So you are proposing that we just upgrade all the roads to highway, which is not possible, right?
Limit the number of GPUs and SSDs per node and then just stack them on top of each other.
Well, then the outgoing bandwidth is going to be a problem, right? So, but similar to that, right? So for the NVIDIA part, they automatically solve the problem by putting a bridge between GPUs, right? NVLink, right? And there's also PCIe P2P version of NVLink, right? And in fact, on the PCIe SSD to the GPU part, the bottleneck is on the SSD performance, not on the GPU side, right? And in fact, there is a drawback of using GPU to SSD direct transfer. Can some of you think about it? What's the drawback of that? Well, there are several drawbacks of that. Software, yeah, except for, so saying that, okay, if I don't need to modify the software, what are the other drawbacks of using GPU direct? No, you don't have to add new wires, right? What's the problem of that? So right now I'm like navigating you guys through why this is a failure idea. You know, originally when I published that paper, I thought it's a good idea. And nowadays I start thinking this is a terrible idea. It's never going to become useful. Okay, what do you think?
Energy?
No, energy is better because you don't have to go through the main memory, right? So that's the pros, right?
Maybe the performance would be worse than the current one.
Why? Under what situation? But our demo, it shows it's better, right? But under what situation it will be worse? You're right, the performance could be worse, but there are cases where it could be worse. What is that?
Are we assume like what would happen if the data that we want from the SSD is not necessarily right next to each other?
Isn't that the same as the problem of the CPU version?
Yeah.
Right? So that's not a reason. What else?
You have to look into every single SSD rather than, well, no, you just have a file system.
Why this idea failed? At least do not fly. Like CUDA has been successful on a lot of things, right? CUDNN, right? But why just CUFile, right? Like we heard about CUBLOS, CUSparse, CUDNN, right? Why not CUFile? What's the problem with that?
Is it a hardware problem?
No.
Oh, okay.
Okay, let me give you a, okay, what do you think?
Does it have to do with the fact that like people don't generally store all of their data in like a file in like just
Okay, saying that I'm always going to store the data back as a file.
Okay.
And let me give you a hint. Operating system, okay, so this idea, right, is basically bypassing the operating system. So you are going to lose all the good things and the bad thing from the operating system. So when running this like GPU application, what are the good things that we still might want from the operating system? Right? A lot of people, right, they just plan that we don't want this, but they never remember there are good things about that. Paging is good in what perspective? Say again?
You know like where all the data, so you know, like I said with the SSD, you know where each data file, which part of the computation you need, you can just kind of pull it and send it.
So demand paging, but you can still do that with GPU SSD, but smaller granularity, right? What are the things that you would miss if you don't have an operating system in this process?
I was thinking that like since you're kind of bypassing that operating system, you're kind of losing the benefit of virtual paging, so you need to know like a lot more of like how memory is structured, and so it's like gonna hurt like her programmability, something like that.
But from the demo that I show you, do you think the programmability really affects that much? Right? I just need to add a few function codes and I'm good, right?
If a process, like, I guess if the process that's happening suddenly dies, like all the memory management that the operating system does, you now have to like kind of do that again, but now have like the GPU handle it. I don't know. Is the CPU aware of like the fact that I know if I'm like.
So any GPU process is still managed by the CUDA runtime, right? So the CPU or say the CUDA runtime would at least know and doing things accordingly. Well, but if we do it right in the CUDA runtime, right, you can still do it, right? And that's the whole purpose of why we have this CUDA runtime, right? So CUDA runtime can do it. What else? Your operating system teacher is crying.
If someone, no, I was gonna say security.
What?
Is it a coherency issue?
No, I'm just only talking about it's not a coherency issue. Yeah, what does the OS give us, right? Like, it's not just like overhead, right? They must to have some good things, otherwise we don't want it. Like, okay, let me give you another hint. What benefits do you enjoy from the file system? That's one thing. And the other thing is that, what if we have multiple GPU processes? No. Okay, each one have a virtual address space. Oh, so what kind of problem would that cause? Okay, so how does GPU handle multiple processes right now? It can only run one kernel at a time. So what if I need to run another kernel from another process? I have to wait one kernel complete. So what are the situations that I would need to have one kernel complete? So saying that right now, I'm done with one kernel. What am I going to do after that? Like, okay, I finished the computation part of that kernel, and what am I going to do with that part? What? You have to output somewhere. Okay, somewhere. If it's GPU direct, where are you going to output?
SSD.
The file, right? And how fast is that? The last time we learned about SSD writes, is it quick? Okay, saying that even though it's quick, who is the bottleneck? PCIe bandwidth, right? 4 GB per second, right? Even though, okay, SSD performs some kind of optimization, I allow you to write to my internal buffer directly instead of to the SSD array directly. 4 GB per second. How fast is it writing to the DRAM? Who is the bottleneck? When you write to DRAM, who is the bottleneck? No, CPU is not. The PCIe bandwidth between GPU and CPU, right? But even with that limitation, 16 lengths is 4 times larger than the bandwidth of SSD. What does that mean is that if you are allowed to write a main memory buffer when you want to switch out a compute kernel on your GPU, it's going to take 25% of the time only without GPU direct. So if you have a lot of GPU kernels that you want to schedule on the same GPU, using GPU direct is actually a terrible idea because it would increase the amount of time when you are switching out. And it also means when you are switching in, it has the same problem. You have to launch the GPU kernel first, and you use the slow 4 GB per second performance in reading at a time your GPU kernel is scheduled. However, if you don't do this, what you could do is that before the GPU kernel is scheduled, I read a file when the GPU kernel is running using my CPU, put it in a main memory buffer. And at a time when GPU kernel is running, I can copy it with 4 times performance, right? So if you are only going to run just one kernel at a time, then you can actually get performance gain, but not to the degree that you would imagine, because as we said, the bandwidth between GPU and main memory is a lot, right? So it turns out we are seeing only like 20% to 30% of increase in performance with single compute kernels. Although we said this is targeting at data centers, but thinking about the data center perspective, we actually want to maximize the utilization of the GPU because GPU is so expensive. So we want to schedule as many processes as possible on the same GPU to save our money. So if you have an optimization that will lower the utilization of your GPU, that's actually not a good idea. So as you can hear, there is no strong incentive for single GPU, single process performance, 30% only, and plus the overhead of modifying all the programs. However, it would be harmful in a data center use case, even though originally we think this would reduce the traffic, right? And actually, it's even worse. So if you are reading file from the SSD to the main memory, the virtual memory abstraction has something called page caching, right? So although, like for example, if I'm currently not reading the whole file, but what the operating system can do is that I would predict what you would need later. So I would use whenever time the PCIe bandwidth is free to read as much data as possible from the SSD to my GPU, to my main memory, to the page cache. So when your GPU wants the file, the whole file is already in the memory, and you can go to the main memory, go to the GPU with 4 times the bandwidth than directly reading it. So it turns out, if you put all this thing together, the benefit you can actually get from implementing this driver, from modifying your application, is very minimal. Right? So that's why, in the very beginning, it sounds like a very cool tool, but nobody is using it. Because at the time, we only think this is cool. We only think since NVMe can do peer-to-peer transfer, we should be doing it. But then it turns out, if you talk to people, and we do have some incentive, like as you said, 30% performance gain, and 30% is actually good enough for you to publish a paper. But think about the real scenario. There isn't a lot. There isn't a lot to do. Right? Okay. So that's the failure story that I have. Now, we still have the trouble of limited bandwidth between the SSD and everything else. Right? So that's one problem. And the other problem is that if you observe, like based on MDOS law, in the past, the major overhead when performing persistent storage access is the device itself. But right now, if we keep making our device faster, then the time we spend in software is actually going to be a lot more. So this software means the operating system management, like creating NVMe commands, looking up the real location of your file in the logic block address, performing protection, checking the permissions. Those are going to take more time than access the device directly. So again, that's why we need near data processing, right? Near data processing is, again, bypassing the operating system. But instead of sending stuff out like GPU Direct, the computation is done locally. So there is no limitation from the external bandwidth. But again, before you go do this, where do you see the opportunity of in-storage processing?
Probably in like a database or something where like you are, although the processing power is applications like the memory isn't is not as fast. So I guess you can only do it when there's like not too much computation. Because if the computation takes too long, since the processor is slow, and like and then and then I feel like it needs to be able to at least after the computation, at least it should have less data that you need to like transfer. Reduce the I think your data processing would your data processing would make sense if the workload we're doing could be done with the processing element that we put in there.
requires a lot of implementation, that it might be easier, it might be better to just set something like policy.
But it allows you to do work.
Add this, right? Nothing very complicated, right? Like, and if you do that a lot, that's going to really slow down performance, right? You kind of bandwidth, right? Because you got to send it over there. Each and request, right? And you also got to send it back. So again, I think it's just like mainly like.
Yeah, so to address this, both we have to send less requests, and we
Well, I
also
think it's like we can't. I think it's like, you can't just assume something less.
All right, where do you see the opportunity of in-storage processing, by which we mean we put processor near storage? So now let's revisit this idea. Is this a good idea? Right? And where do you see the opportunities right there? Like again, I'm the veteran of this topic research. So I do have like mixed opinions on this. So if you don't like it, feel free to say about it. I won't feel offended at all. But if you really like it, let me hear it. Maybe I will be thinking about doing it again.
Yeah, it has a potential where you transferring a huge amount of data by doing simple computation. So I think when you're data processing, you can only do very easy computation. So if your purpose is like very easy computation and you want to save your effort from transferring to GPU and doing that simple computation transferring back, I think you can do your data processing in that.
Say again?
So your computation is simple. So you don't
Simple computation. Why it has to be simple?
because I think for near data processing, the AOUs will be
Okay, you cannot put powerful processor near the, like you are not going to put a GPU inside your SSD, right? Well, although it's kind of interesting, AMD, I feel like I used to be a good friend of AMD, but right now I feel like every time when I teach such kind of class, I feel like I'm the criticizer of AMD. AMD once had the concept of SSG, solid state graphics. So what does that mean is that instead of putting just DRAM on the GPU, they actually put 4 terabytes of NAND flash on the GPU. So the good thing is that you don't need, so the thing is that you don't need to handle the case where you would never or seldom suffer from the case that like CUDA main copy, CUDA malloc, but you failed, right? Because you basically have 4 terabytes of device memory that you can use, right? But do you see it popular, right? So there are quite a few reasons for that, right? So like, although I do want to say you don't put SSD, put a GPU inside the SSD, but AMD once does that, right? Once did that, right? But the thing is that in general, like for solid state drive, we just want it to be cheap and small and power efficient, right?
So going to say, I don't know how it's really effective this is, because going back to say about programmability and kind of like that way, if you're going to be like programming, it's going to be kind of hard to do given the fact that it's not as easy to do with CPUs, right?
Mm-hmm.
So that's like a major limitation because now you have to consider it that way, right? And so if like you would have to be having like a really like large software loss, like software overhead, to even consider doing this, because again, it's going to be complicated setup, right? Costly to kind of implement like just through hardware, right? So I mean, like unless you're having major like especially like in like a data center, unless you're having like a really bad like a software overhead, I don't think it's really good at the idea.
Okay, so but you mean software overhead? You mean when you say the software overhead is like a programming overhead?
I mean, I'm thinking like specifically like we're talking about like OS a lot, like the context switching between like when you're just trying to get.
Okay, so but the whole thing about in-storage processing is because when you do the processing in storage, it's not managed by the operating system, right? It's directly managed by the firmware of the controller itself, right? So that's actually the main positive side of using in-story processing.
That's what we're talking about.
Right.
You bypass it. What I was just thinking about was, it's just the cost of implementing all these smart SSDs as well as the programming all these SSDs.
Okay, so you're criticizing about programmable, program-related stuff. Okay, so program-related stuff is a bad thing. What else? Any idea? Okay, if not, we can talk about this more in the next lecture, because I do have a lot to share. I feel like I'm sharing my failure story these days.
Yeah, we're learning.
You are learning. What? You
I was thinking of an application, but that's fine.
talk about that.
I think this would be really good for things like that are kind of large amounts of data that have simple pre-processing steps.
Mm-hmm.
So, like in certain graphics.
Yeah, I think what he said.
Yeah.
Right. Okay. Okay. So good thing is that if it's simple processing, but is it just simple processing? We can talk about that later, right? Okay, but more importantly, some of you were asking about what do we expect in final presentation. First of all, it's always good idea to remember why, right? So 3 to 5 minutes talking about the why, and what has been tried, what you have been done, what have been proposed, 5 to 7 minutes, and now experimental result, so that I know you guys did explore something, right? And it's okay to have negative result, and in fact, I feel negative result matters. At some point in my life, I was thinking about I should organize a conference that only accept negative results. And the reason is because a lot of cases we failed, but we are so shy to talk about our failure stories to others, right? We never agree, why am I suck, right? Like, and the thing is that the consequence is that then people repetitively try those terrible ideas. And well, I shouldn't call it terrible idea. Like, it looks clever, but at the end, it's a terrible idea, right? Like NVMe P2P. That's a clever idea. And that's a neat idea. It sounds like it would help us. But the thing is that in real cases, we seldom find a case that it will be helpful. Then it becomes a terrible idea, right? So we need to share more about this kind of story, right? For example, a lot of cases people will think about, okay, I should use cuSparse to accelerate large language models because it seems to be pretty sparse. But is it really a good idea, right? And my personal experience is that it's a terrible idea, because with hardware acceleration, dense matrix multiplications are actually a lot faster than sparse matrix multiplication. Unless you can make cuSparse or sparse matrix multiplication really fast, using sparse matrix multiplications to replace existing multiplications in AI machine learning is actually a pretty bad idea, because you are going to get worse performance, right? So if you want to solve that problem, you really need to address the slow sparse matrix multiplication problem, right? But the thing is that nobody ever shared that terrible idea, because they don't get a good result. The reviewer rejects their paper. So nobody knows that, okay, there is another problem we have to solve first, right? So what I want you to do is, if indeed you get negative result, share it. But it's not just about sharing it, figuring out the inside at the back. Why it's negative? Why is it not as good as you would imagine? And more importantly, if we fix X and Y, would that be a good idea, right? So if you can have that kind of piece in your presentation, then it's actually a more meaningful research than those successful ideas, because they never tell you the failure story of them. So it turns out people keep doing the same thing again and again wastes a lot of time, right? So I do want to hear the insights you learned, and hopefully that will be another 3 to 5 minutes. All right, so those are the high-level questions.
Do we not have a write-up?
We don't have to write up.
Oh, okay.
We don't have write up. It's all about presentation. All right. Other than that, enjoy the rest of your day. I will see you